Hello student, in this video we are going to discuss frequency response analysis. First of all, frequency response analysis means this is the response of the system for sinusoidal input. That means the definition for frequency response is this is the steady state response of linear time invariant system for sinusoidal input. For example, if this is linear time invariant system, if you given any sinusoidal nature of input, so if you are exciting your LTI system with some sinusoidal signal like sin omega t, cos omega t, sin 2 omega t, cos 2 omega t like that, then you will get the same signal out at the output. You can observe that amplitude and phase are vary, but the frequency is not going to vary. When the frequency is not going to vary means that you are getting the same signal at the output with increasing or decreasing amplitude. That increasing and decreasing amplitude and change in phase due to the system characteristics. Okay, so that increasing and decreasing amplitude and change in phase due to the system characteristics. So coming to here, see, our input is sin omega t and output is a sin omega t plus phi. So coming to A, so A is nothing but the amplitude and omega is the angular frequency of the input signal. Same will be maintained at output also. Okay. That means the frequency will be maintained at the output also. And coming to phi, so phi is the phase of the system. Because of the system of that system, how much phase because of that system how much phase of this input signal is taking, so that much phase we will indicate here. So for example, if we are considering a sin omega 0 t is the input signal of the system, that means RT equal to a sin omega 0 t. So after considering our signal, what we are doing? We are giving the signal to our LTI system. So now I am considering the LTI system open loop transfer function as GS. Okay, that means this GS. So here, as we are giving the input signal as sinusoidal signal or a sin omega 0 t, definitely we can substitute s equal to j omega in our transfer function. So now onwards we are going to substitute s equal to j omega. So gs equal to gj omega, and now we can represent our transfer function like in like this in terms of magnitude and phase. So first of all, here see, here we substitute omega equal to omega 0 in this gs gj omega. Okay, so if we substitute omega equal to omega 0, then our open loop transfer function is gs equal to gj omega equal to gj omega 0. Okay, now see, if you substitute s equal to j omega 0 in our transfer function, so now onwards we are going to substitute s equal to j omega 0. So g s equal to g j omega 0, and now we can represent this transfer function like in terms of magnitude and phase. That means in this way. Okay, this is our magnitude term, and this is our phase term. Okay, so here in this equation we put omega equal to omega 0, then this equation will be like this: g j omega 0 equal to g j omega 0 mod of g j omega 0 and angle of g j omega 0. So this is our magnitude and this is our phase term. Okay, so see, this is our transfer function, open loop transfer function. This is our open loop transfer function. Now let me clear this thing. So this is our open loop transfer function. So we can represent our transfer function like in this way. So this is called, that means this is called, in our transfer function, this is called magnitude spectrum and this is called phase spectrum. Okay, so see, this is our magnitude term or magnitude spectrum and this is our phase spectrum. Now let me clear these things. Now see, for example, if we represent CT, that means output signal, then how we will get output signal? So see, if we given a signal to the input of the system, so according to the system characteristics, the amplitude is going to vary and phase is going to vary. So how we can write the amplitude in terms of magnitude spectrum, and that's why we need to get the amplitude. Okay, and now coming to phi part, that means phase part, and so this phase angle we need to consider. Okay, this phase angle. Why? Because g j omega is the transfer function of the system. That's why for magnitude, in terms of magnitude, we need to get the amplitude, and coming and in terms of phase we need to consider phase spectra. Okay, so according to transfer function, the output signal is going to this. Okay, ct equal to mod of ct equal to a mod of gj omega 0 sine omega 0 t plus angle of gj omega 0. Okay, so in terms of multiple of magnitude spectrum or multiples of magnitude, so ct equal to like this. So that means if we observe amplitude will vary according to system transfer function, so that's why this output signal amplitude can be calculated by taking magnitude spectra in multiplication. Okay, so we can see input signal is multiplied with magnitude spectra, and here coming to phase angle, we need to consider the phase of the system. So this will be our output signal, and in this signal omega is not going to vary. The frequency of the signal is not going to vary. That means we are getting the same signal with increasing and decreasing amplitude and change in phase. So this about the frequency response of the system, and this frequency response of the system nothing but the steady state response of the system. Frequency here is giving in terms of sinusoidal signal. Okay, so this all about the frequency response. Now see what is amplitude. The amplitude of the output sinusoidal signal is obtained by multiplying the amplitude of the input signal and the magnitude of gj omega at omega equal to omega 0, and the phase of the output sinusoidal signal is obtained by adding the phase of the input sinusoidal signal and the phase of gj omega at omega equal to omega 0. So we can write angular frequency omega 0 as shown below. Omega 0 equal to 2 pi f0. F0 is the frequency of the signal. Okay, so rest of this frequency response analysis I will discuss in the next lecture. Okay.